Welcome. This is Team ExoBuzz, and we are on a mission to explore exoplanets outside of our solar system, take photos, and send them back. Hello, my name is Drew, part of Team ExoBuzz. I'm going to be explaining the trajectory of our rocket launch. So we are going to be using a 4-stage rocket, where the first stage will launch us off the planet Earth. We have the second and third stages to break Earth's gravity, and the fourth stage carrying our satellite will take us all the way to the exoplanet. So, launching from Cape Canaveral Base, closest to the equator, to get the most rotation out of Earth, we're going to be launching with Earth eastward rotation to get the most speed out of it. Moving on over to our first slingshot point with Jupiter, where we will approach Jupiter at 500,000 kilometers, coming in at an initial velocity and increasing our speed using Jupiter's gravitational pull to pull us closer and give us an increase. So we'll end up leaving the solar system out at an angle towards the exoplanet once we've slingshot around Jupiter.
Hi, I'm Frank, and I'm in charge of propulsion and power systems. I've chosen the Vasimir propulsion system. It's a new technology headed up by the Ad Astra rocket company in conjunction with NASA. It's a type of ion drive that uses superconducting magnets for containment and RF antennas to ionize the argon gas as it's passing through. A conceptual advantage of the Vasimir rocket is that it uses these superconducting magnets for containment throughout the rocket, reducing thermal losses of energy and also increasing the unit's lifetime. I also did some calculations of the, given this propulsion system, the time of flight that would be necessary, and balancing that with the amount of fuel that would be necessary on the ship. Here I used the relativistic rocket equation. As you can see, a change in velocity requires an arctangent relationship with the ISP, which is a measure of the fuel efficiency, and the mass ratio that will be necessary on the ship. I calculated that with 87.7% of the ship being fuel, we would be able to make a trip of approximately 300 years, give or take 2 decades, to make it to Epsilon Eridani. This engine, however, requires a large power requirement, which would probably be greater than 1 megawatt. This is actually what's the up-and-coming newest version of Vasimir will be requiring is 1 megawatt exactly, and we'll probably require even more for our trip. To provide this, we'll need an onboard nuclear reactor, which actually has been a past subject of research. The SP-100 program back in the 70s and Project Prometheus up into the 90s. Both were canceled for political reasons and because NASA's focus was shifting. But presumably with such a large project in the works, we would be able to throw lots of funding into it and have a very good system. That's all.
Hi, I'm Blake Marshall, and I was responsible for the RF side of the transmission of our communication system. And first of all, I laid out just the basic, what it's going to look like in space. And we're going to have a 20-meter diameter dish on Earth, and we're going to have a 10-meter diameter dish in space on the satellite. And they'll be approximately 10.5 light years away. In order to analyze this situation, I simply used the link-budget equation, assuming our carrier frequency of 7.2 gigahertz. And after the analysis, we can find that we'll get about a power of negative 290 dB. And in order to ensure that we can actually recover the signal, I compared it to what our noise power would be, which would be approximately negative 350 dB. From this analysis, it's clear that we'll have enough signal-to-noise ratio in order to reconstruct the signal back on Earth. The other thing we should mention is that this one antenna on Earth won't be in constant communication with the antenna in space and the link. So what we'll do is have the communication actually on a loop, so that the antenna is constantly broadcasting, and we will be able to completely reconstruct the signal, even though we're not in constant communication.
Hi, I'm Vidisha, and I'm going to be talking about the communication system. First, we can discuss about the modulation techniques. For our mission, we are going to be using the QPSK modulator, here. That's quadrature phase shift scheme. In this technique, we take the data signal and split it into two parts and send it to two channels, that is the in-phase channel and the quadrature phase channel. Here we can see that the carrier, it modulates the first stream of data, and for the second one, the carrier is 90 degrees out of phase. And then both the streams are combined and this data signal is transmitted. And at the decoder side, it is decoded in a similar fashion where we use the carrier signal, which is like one channel it is a cos sign, and the other channel is the sine phase. So this is about the modulation technique. So this is very efficient because we can send 2 bits per symbol, so we get a higher data rate. And the next thing that we can talk about is the channel coding. Our channel coding should be very efficient as the data has to travel through a long distance and long path, and it should not be corrupted by the time it reaches Earth. So what we are going to be using is the turbo code. This is very efficient as it's one of the few codes that reaches the Shannon capacities. And here is the turbo coder. In this technique, the input is encoded twice. In the first channel, it is just directly sent to the encoder, while in the second part, it goes to an interleaver. And interleaver is generally just scrambles the bit. So what happens is that we have two outputs, that is two encoded parts, and at the receiver side, the receiver decodes both of these, and like whichever one has a higher weight, it takes that, and this way we can exactly pinpoint as to where the error is, and we can exactly correct that part. So this is very efficient in that manner. So this was our modulation technique and error correction technique that we have used. And the next thing that I'm going to be talking about is space hardening. As we know that our spacecraft has to go from, it has to travel about 10 light years. So what happens is during launch, the spacecraft experiences high temperatures, but when it's outer in space, it experiences freezing temperatures. So it has to be able to function in both of the extreme conditions. So what we are going to be using are techniques such as heating systems and cooling systems. Well, like for example, during the launch, we can have the cooling systems to function. So in that way, we can have the systems to be like they can be in a optimum temperature and they can work, they can function properly. But when it goes to deep space, we can have the heating systems to switch on, and that way we can have our systems function properly. And we can also do another thing is that use redundant systems. One of the ideas that we came up with is have multiple computers do the same computation over and over again, and we check for consistency. If a particular computer is giving some other answer or some other output, we know that that particular system is something's wrong with it, so we can just kill it. So this way we can have redundancy and have better functionality of the system. And another thing that we plan to use is shutter mechanism. This thing, what it does is when there's high temperatures outside, it kind of just opens slightly, so lets a bit of the heat inside into the system. But when there's freezing temperatures outside, it just shuts and traps the heat inside. So this way we can maintain an optimum temperature for the system to function. So these are some of the mechanisms that we plan to use.
Okay, my name is Adam, and I was responsible for the data compression portion of our project. And considering that we have to take pictures of the exoplanet and send them back, we need to do this at a smaller bandwidth and smaller size, so we're not having errors in the image or transmission. So there's multiple ways you can do this, but I'll just discuss one. It's probably one of the most simple ways of doing it. So here's a block diagram of the encoder above. You start with an image, and it's a color image, so you convert it to YCBCR, which allows for easier compression, because you can downsample the chrominance channels and really not be able to tell from the human eye. And so then you take the two-dimensional DCT, and then keep the upper 1/4 low frequency coefficient. From there, you can vector quantize these coefficients and perform one-length encoding on them. And my process for the encoding took a 175 KB file and converted it to around 4K. And the second part is some vision. In a spacecraft mission that's as far and as long as ours, you're probably going to have some instances where you run into stars and planets and just general space junk. So here's the basic algorithm to avoid these. Basically, for light-emitting images, we're finding the lightest pixel in an image, finding a center of mass, storing it, and then comparing these to determine whether we have to move our spacecraft. And if it's not a light-emitting object, you basically use a system like radar, and that will constitute a decision criteria. So this is our data compression and vision tracking algorithm, and that's all.
Once again, we're Team ExoBuzz, and we'd like to thank you for watching this video. And before we finish up, I just want to do a quick overview of our timeline and some of the milestones we're going to try to complete. And pretty much by year 4, we're going to try to actually launch our satellite. And you'll see that'll include all the assembly and all of our systems that we're going to need on the satellite. And then we expect it to take about 300 years in order to actually arrive at the exoplanet, and as well as about 10 years traveling the speed of light for the signal to get back to Earth, where we can finally get our first photograph. In conclusion, I just want to go ahead and thank Dr. Durgin for putting on this class, and thank you for watching this project.